Yes, there we go. I want to recap what we were doing last time. Let's see here. Distributions. We had scratched the surface of this last time. This will take us. This is the rest of the course. I mean, essentially, this idea of probability distributions is the rest of the course. It's a way of looking at an entire population of data in a very, very efficient way. Sometimes you don't want to do that. Sometimes you don't. Sometimes the sample is good enough. Sometimes the sample of a very small population, which can be viewed as a sample, is good enough. But if you have a very, very large population, or a predictable population, this is kind of the way to deal with them. So when I say probability distributions, and you think back to last Thursday, which I know was like 3.5 months ago, what do you remember about anything you remember from last Thursday? I'll give you a hint. It involved rolling a die. What do you remember besides the rolling a die part? What was the whole point? Lauren, go!
I remember P of X.
You remember P of X? That is fantastic, my friend. What was that?
Likelihood of random variable.
Nice! What's a random variable?
X.
Good! So there was an X and a P of X. I think we did this with them, yes? We made a chart up. So what Lauren just defined for is P of X. This is the likelihood of a random variable X. Love that. What's a random variable?
X.
Good, good. Why do we call it a random variable?
It's random.
What's random about it? You roll a die. Nothing random about rolling a die, is there? You're either going to get a 1 or a 6 or a 2 or a 5 or
4, 3.
4 or 3. Natasha, you're going to say, go ahead.
Everything's random.
Everything's random about it except for the range of, you know what the range of values are, right? You know you're going to get between a 1 and a 6, but what? What's random about it?
Where you'll land in the range.
Exactly. You don't know at any given moment what you're going to roll. So basically, these random variables are somewhat determined and somewhat random. The randomness is you don't know which one you're going to get. The determinedness is you know what their values are overall, you just don't know which one's coming when. You do, however, know something about them, and that's what Lauren was getting at here with the likelihoods. What's the chance? What is the chance, if you roll a single die, of rolling a 3?
1 and 6.
Why?
Because there's 6 dice and there's 1 3.
Okay, good. So if I was to try to explain that to my neighbor as far as betting goes, would it be smart to bet on 3 and only 3 if you were rolling a die? Lots of gambling involves rolling a single, a double, triple, or quadruple die. Yahtzee's 5 dice, and so forth and so on. Would betting on 3 be a fairly good? Carolyn got an A in the course last year, if I remember correctly, last week. I handed you the dice, said roll a 3, you get an A, and you roll a 3, and you didn't leave, you came back. I appreciate that. Wow. But what does that 1 and 6 mean? There's 6 outcomes, right? 6 outcomes. One of which is a 6. And that's a perfect definition of what a die is, because it's a random number generator, 6 equal outcomes. What if we say there's an 80% chance of rain today? Actually, there's a 100% chance of rain right now because it's currently raining. But let's say the weather person says there's an 80% chance of rain. What does that 80% mean?
Well, over an infinite number of days, at some point it's going to even out. Well, there has not been an infinite number of days for the weather people. But I'm saying for like the dice, the 1 in 6 chance, over an infinite number of rolls, over that long period of time, the 1 in 6 is most likely.
I love the fact that you said infinite, Lauren. You just triggered something. Everybody got some dice? While you're getting your dice, I want to show you something I built. I wasn't gonna use this actually, but you just triggered a thought in my mind. Well, there you are. So you can't see that. Okay. So let me back this out a little bit. So what I want to do is I want to show you, I think, and Lauren, I love the fact that you use the word infinite. I love that. Because technically speaking, if you're going for mathematical perfection, you have to use the word infinite. But you corrected yourself and you said, well, there haven't been an infinite number of days with the weather forecasters. But you know what? There have been so many, they can treat it as infinity. More on that in about an hour and a half when we get to our last experiment of the day. The idea of you can stop past the point because the results aren't giving you much more of a return. data-wise. Thank you for that, though. So what I've done here, it's similar to what we looked at last time with Excel with rolling a single die, but it's going to roll 6 of them. And up here, in 6, you can't see them right now because I think they're all on 0. There's 6 different colored dice that are acting like a little chart that are plotting the probability of rolling a 3. So the probabilities are between 0 and 100%, so it's 0% to 100%, there's 50. Lauren just made a claim that the probability of rolling a 3 is 1 in 6, which as a percentage is what? What would that be as a percentage? Roughly 17, good, very nice, just shy of 17%. So as I roll, what we should see is these dice right here bobbing around and settling in, as Lauren said correctly, over infinity, right? Over infinity. So let's start rolling. Let's start rolling. And you see what's happening? We've got some experimental digressions, I guess. Some are going high, some are going low. But look where they're headed. Look where they're headed. Some are above 20% right now. It almost like it's up around 30. But let's let it go off, just like Lauren said, to infinity. What's beginning to happen to those probabilities?
It's kind of going up.
Look, here's it right here.
They're kind of evening out.
17, 19, 14, 11, 17, 17. Okay, here we go. What? So say that again. Was that Carol? I think I recognized your voice.
They're grouping together.
And why would they group together?
Because the more rolls, then the more chance they have of showing that average.
That 1/6
that probability
is a long-term average. I love the way you just said that. That 1/6 is a long-term average, which means it's not going to show up until the long term. Now, unfortunately, I can't. Oh yeah, so it's slowly going that way. Let me do this. I'm going to click on this. Let me format this. Let it go out. Maybe let's let it go out to like 5,000. There we go. And I'm going to get my stapler. I'm going to let this thing hold itself down and run off to infinity for 5,000. And we'll see how it looks. Is it going?
Technology. Stapler.
Well, if I ever took a Visual Basic class, I wouldn't need the damn stapler. I just run it 5,000 times. Haven't done it yet. I think we're going. So now, right now, it's doing its thing. The dice aren't going to move. I don't know why this is. Certain computers on campus will update very quickly, graphically. These update beautifully in the chart. 17, 17, 19. That one's too high with the 18. Okay, 15, too low. 18, too high a smidge. Let's let them run a few thousand times. Right now to the 1,000. We'll come back to it. Did it correct the 17?
Just about.
Good. They're doing their corrections. I mean, they have to because of what Lauren just said. We're letting them get far up. Did it move? Did they move or they've been stuck there? Did it move a little bit? I can't tell because I keep turning it around. We'll pause it, we'll mute it, and come back to it, okay? But I love what Lauren just said, because what she said is the most important thing about it. It doesn't guarantee you that in every 6 trials you're going to get a 3. It guarantees you out of every 6 trials you're going to get a 3 on average over time. But that does not mean you're going to go 1, 2, 3, 4, 5, 6, and in there's a 3. 1, 2, 3, 4, 5, 6, and there's a 3. It means if you look at all the results spread out in front of you, you can rearrange them so it goes 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. But they don't come in that order. They can be rearranged to that order, but they don't show up in that order. As a matter of fact, there are going to be quite a few times where you get 5 or 6 3s in a row. And you start going, what the hell happened to that die? Nothing. Randomness happened to that die. You don't know what you're going to get, right? You say, what was the 1 in 6 chance of getting anything on any given roll?
There's also a 5 in 6 chance you're not going to get.
Exactly. But that doesn't mean you can't get a bunch of 3s in a row. It just means it's not likely to get a bunch of 3s.
Why would you be careful? That's
Well, by the time you get out of this class, you'll understand the answer to that. And if you haven't, to your Lauren's question, why would you ever gamble? The thing is that we gamble every day of our life without going to Vegas.
No.
I mean, you drove here today. That's a gamble. You walked into this building. It's a gamble. You purchase insurance sometimes. It's a gamble. Everything is based on the idea of gambling. It's also based on the idea of averaging the gamble. And that's what kind of the point of today and also Thursday and the rest of the course is all about. Averaging the gamble. And being able to metric it in some way. So thank you for that question. Hopefully the answer will come over the next 4 or 5 hours together in the end of class. Good? So we love this experiment. We were able to average this. We were able to, speaking of averaging, and when we took the average, and sometimes important but not always important was the standard deviation. I'm going to put him down here in parentheses because sometimes he's important, sometimes not. It depends on the shape of the distribution. We still only like the standard deviation when we've got roughly bell-shaped data, because honestly, any other times it gets too skewed to talk about. Do you remember the symbol that we can call him now? Remember that goofy little, like sideways look at 6? That's lowercase sigma. Your TI reports that back to you. It does not give you a sample standard deviation anymore, because your TI knows you're not giving it a sample standard. You're not giving it a sample. You're giving it population values. That's pretty slick. That's pretty slick. Yeah, it's pretty slick. So your TI knows that now. It knows that because you're giving it population percentages. We will argue those in Math 244. I love arguing them, actually. I love when students argue back with them. It's fantastic. I shouldn't say argue, discuss them. Why they shouldn't be called population percentages without a margin of error. To which Lauren replies, just go out and do... I'm sorry, you're thinking about something else. Go out and do more trials. Sorry, you're thinking about lunch. Go out and do more trials. We'll go back to that. We'll go back to that. We'll ignore that small point, which is very important for today anyway. The average, though, I don't ever want to ignore this guy. Remember the Greek letter for him? We briefly mentioned him last time. If you don't, it's okay. Oh, somebody does. Be brave. They heard it. Remember that? Mu. That's him. Think of a little kid. Mew. Mu. Remember why it's called mu? I think we talked about this. Why it's the letter M? Because it matches with mean. Boom. Matches with mean, just like matches with standard deviation. I mean, they try to be logical whatever possible mathematically. Pi, 3.14, you know why it's called pi? It has to do with a circle, which is C, right? But pi, they used to call the distance around a circle a perimeter of a circle. Perimeter. And they just, when we started calling it circumference, they didn't change the constant, they just left it at pi. And that idea has been around forever. In the Bible, there's a reference to, I love this one actually, not that I'm a huge Bible reader, but there's a great one that says, the distance around a well is 3 times as much as the distance across. That's freaking awesome! That's pi, 3.14! 3 to 1. Hot damn, yeah, it's the book of Numbers, coincidentally enough. I think it's great. I love that, it's right there in the Bible. So you can think about how old some of these constants are. Now these constants are much, much younger. I mean, statistics has only been discussed seriously for a couple hundred years compared to thousands of years for arithmetic and algebra. But nonetheless. Cool? That's about as far as we got. And we're going to use technology again pretty heavily today. But I want to do some more data collection in class. And also comparisons to technology. Ooh, before we go on, let's see how we're doing. Also, what have you on the camera again today? There you go. How we doing? Well, the dice are gone. They're off the screen because we're past 5,000, I guess. Yeah, we're up at 8,000 now. 17, 16, 16, 17, 17, 17. Let me stop it real quick. Let's stop it real quick. And we're at 8,000. Let me adjust the axes again. Let's go out to 10,000 so we can see it. We'll scale them by 1,000. Okay. There they are. All together. Right there at 16, 17%. Right where they should be, yes? They should be rounded to 17. There should be probably more close to 17 than 16. Oh, look at that. Honestly, 2 are at 16, 4 are at 17. If you think about it, 16 and 2/3. That's what the decimal should be, 16.66666. So 2/3, there should be twice as many close to 17 as away from, right? Does that make sense? So it's actually, now they're going to continue to flip-flop. It won't always be the same 2 as it goes off to infinity, because sometimes we'll have a few more 3s on average in a small block of time, but they'll get caught up later. So they're still fluctuating. There's still fluctuation within those. It's just so small now that that error is becoming meaningless. So that's when you said infinity, and Lauren, it was perfect. It's infinity enough, if that makes sense. Hopefully that makes sense. All right, let's change the experiment to Austin, if you don't mind muting the screen. Let's change the experiment. Let's use 2 dice now. Because honestly, a single